There we go. And we're recording. All right, so concerning content, any questions? Lisa?
Tell people about solving master set 6's question 2.
Master set, which one?
Master set
6, question 2.
Like my biggest.
You have it right there in front of you?
Yes. My biggest issue is I'm not sure how good it is.
Okay, so it starts out when the room is not moving. And so I think one of the first questions is how fast do you need to throw it to get it to the other side? One of the first ones, I can't remember exactly what that falls in order.
Yeah, one of the initial speed.
All right, so, and so that's just a projectile motion problem. I tell you the initial height from the floor, and I tell you how far it is above it, so you know how far it's gonna drop. Since it's being thrown horizontally, there's no vertical initial velocity. It's just a straight up projectile motion problem with something being thrown horizontally. Once you have that, there's a question of how we get the room spinning. And so there's hopefully one of these markers will be dark enough. There we go. So perhaps a little bit more focused. What was the first part, A?
If the room wasn't moving, how long would the ball be in front?
Okay. Well, so I'm just breaking the projectile motion problem up into parts. So the first thing you do is figure out how much time it takes to fall that distance, and then you use that to figure out how fast it needs to go. I assume part B is how fast is it thrown?
Yes.
Okay. And then part C?
The ending velocity, the final
Oh,
velocity.
okay. Still projectile motion problem. And this is something I noticed on the first test for a large number of you. When I'm asking for velocity, a lot of you gave me speed, or at least part of the velocity. Velocity is a vector. Therefore, what has to be part of the answer? Yes. Now, whether you put it in rectangular form with an I hat, J hat components, or whether you put it in polar form where there's going to be the angle at which it's hitting, either one is fine, but there does need to be a direction in there.
I think part of the confusion is a lot of the formulas don't have the vector sign over it, and so it's kind of hard to associate which formula for what.
Yeah, that was my confusion.
Yeah, I think where it doesn't have the vector sign over it, the caret. Oh no, that's the I hat. Just kidding.
Okay. The formulas that I gave,
Yeah, on the front page.
because the textbook doesn't give them. I think the textbook, it seems, maybe I'm thinking of the other group.
As far as like a reference, like referring back to,
I've got it right here.
like if I need to find V, it's like I don't know really which one I need to use.
Well, I mean, in terms of what I gave you, I wrote down the way the book wrote it, and then I put in the ones with the vector symbols, which is the way that I've been writing it.
Okay.
Yeah, textbooks sometimes get fast and loose with the notation, because you're just supposed to know. I guess that's part of the art of the course. I'm sure that's a very unsatisfying answer, but okay, I hear you, and we'll find out what I do with that. Okay. Was there another, you were supporting that? Gina, were you backing him up?
Yes.
Okay. Was there another comment or question, or I felt like there was another voice in there?
No, but I will say I agree because I was very confused.
If you look at the old tests, you'll see basically the formulas that you're going to see. So to give you some idea of what to expect. Yeah, because we've been using this textbook for 10 years. Yeah, I think we went from the Hex book to OpenStack, so we've been, other than that first, I think the first year, maybe first 2 years, after that, we've been using OpenStack, so that's probably a good guide of what you'll be given. All right, so anyway, that question was, what is the final velocity? So it's coming in at an angle. There's a horizontal and vertical component, or there's a magnitude and an angle. Do recognize that I am sticking with standard convention of 0 degrees, 90 degrees, 180 degrees, 270 degrees. So as it's coming in, if you're looking at it like this way, that would be a negative angle because it's going clockwise. All right, Musa, do you have enough to get going, or do you want me to keep sort of hitting the general approach for these?
I think some more elaboration might help.
Okay. What's the next one after, what's the velocity, final velocity?
If I'm going to catch the ball on the outside of the circle, what's the angular speed of the root going to be?
Ah, okay. So basically it's a circle, and you're right here, and you're going to throw something across to that. You know how much time it takes to get there. Now, if you're going to catch it yourself, you basically need to be in that position in however much time it takes for the ball to get there. So that was the angular velocity, or angular speed?
Yes, angular speed.
Omega. Change in the angle over the change in time. So if I'm doing half a circle, what's the angle?
180.
If you just write down 180, though, be careful with that.
80 degrees.
All right. Or
Pi.
usually angular speed is in radians per second, so pi is preferred here. If you do 180 degrees, then you're going to have to keep track of the units throughout. So pi over however much time you got from the previous problem. And you'll get some number. So it would end up being radians per second, or if you went 180 degrees, degrees per second. And then I assume angular speed's the next one, or sorry, linear speed.
Yes.
So you're in a circle, you're traveling around. The middle's not traveling very far. If I think about a circle here, this whole thing is spinning all together. We assume that it's a rigid body and that the time it takes for this part to go all the way around is the same time as it takes for this part, is the same time to take this part. So if I have a spot here, it's only traveling that far. This one's traveling that far, and this one's traveling the farthest. So the linear speed is going to be greatest here, because in the same amount of time, this one travels a farther distance than this one does. And so there's, obviously, so therefore the farther out you go, the faster you'll be moving. If you're troubling visualizing that, imagine with the Dragon's Tail, so the student a couple years ago that this was actually a game that he played as a kid. If we sort of held hands and went, all of us held hands and we sort of went out however far we went, and then I just start turning like this, if we want to keep the rigid line, the person next to me is going to be traveling a reasonable speed, doable, but the person at the farthest end is going to have to be running really fast because they have a lot farther distance to cover. And so if I just do that, I'm not really moving my feet at all, but the person from the outside's got to run. So the farther out you go, the faster you're going. And it's all summarized in the equation that V is equal to omega R, or V is equal to R omega, it depends upon your mood. And the radius, I think, is given, or I gave you the diameter, you can find the radius. Omega, you just found, so find V. And the last one is about throwing it. So at what angle do you need to throw it? If I'm in the spinning room and I just throw it, so this room is spinning and I just throw it that way, recognize that if I throw it straight in front of me, I'm gonna give it some initial velocity in that direction, some component of the velocity in that direction, but the room is giving it a velocity in that direction. So if I throw it, from my point of view like that, that ball's gonna end up being thrown over there. Because I'm giving it a push in that direction, the room is sending it that way at that moment. So in order to get it straight across the room, I have to send it this way. So I'm gonna throw it like that. And so in essence, what I'm doing is offsetting the speed of the room going this way. So I'm going at some speed, just 20 meters per second. I know that's not the right answer, but we'll just pretend. And if I have to throw it this way, so this is the speed of the room relative to the ground. This is how fast the ball is going relative to me. So we'll just say that's 15 meters per second. Well, I still want that 15 meters per second straight across, but I need to offset that. And so I need to throw it so that with a component of 20 meters per second this way, in essence, so those would cancel out. That's the angle I want. And at this point, your life should just feel slightly more complete. Or you knew this already without ever asking any help, and you're thinking, yeah, I rock that. I am a god. That's sort of what the pastor reminds every once in a while. Until you get the next physics problem. All right. Any other questions on this? Other questions?
I'm also a little confused on how to go about solving question 4.
All right, and 4 is. Three masses on a line. Oh, the gravitational force problem. This is using the idea, we've talked about FTOM. And up until this chapter, the gravitational force has been weight. And we can use the formula mg, really nice and simple. Matter of fact, you can use this anytime except g gets really tricky because what is the acceleration of gravity of the Earth with respect to the sun? It's not something that's generally given. We know the acceleration of gravity when something's near the surface of a planet. So when you're dealing with especially celestial bodies or really tiny things, things that are not planets or moons, then we have to use a more generalized formula. Let's see, so the force on 1 from 2 would be g mass 1 mass 2 over r squared. And then r, see that's the force on 1 from 2, so r2 hat, and there you go. So that's the formal writing of the generic gravitational force formula. This is a radial unit vector. Seems like I've talked about radial, well, it would have been in one of the videos at least.
I don't know.
I hat, J hat, K hat, those are, you set them up, I hat is whatever direction you pick, J hat's perpendicular to that, K hat's perpendicular to those two. Radial unit vectors are a little bit different in the fact that there is, the choice is not in which direction is it moving, the choice is what is the central body. It is reference to what. So if I have the mass 2 here, and R2 hat is in reference to that, R2 hat is a unit vector going away. It's not in one direction, in the sense of, left, right, center, or coming at you. It is going away from the center. Negative R2 hat, well, negative still has the same meaning, it's just the other way. So negative R2 hat will be going towards it. So a centripetal force, or let's just do centripetal acceleration, is negative v squared over r hat. The v squared over r, that's the math part of it. The negative r hat is just saying it's towards the center. So if I have mass 1 and mass 2, they're being attracted towards each other because gravitational forces attract. This force right here, this is the force, gravitational force on 1 from 2. Whenever you have the subscripts, the first one is what the receiver of the source, and the second one is the, receiver of the force. That's the source of the force. And so that is, well, the magnitude G m1, m2 over r squared, where r is that distance there. And the direction is towards m2. Now the reason we write it like this as opposed to away from m1, so we're not just doing r1 hat, is, well, because this force is in reference to this. M1 is being attracted to this one right here. And also R1 hat could be referring to in this direction. And then the force of gravity on 2 from 1, negative G, mass 1, mass 2, over r squared, 1 hat. The radial unit vector.
So the first number is the mass that you're measuring the gravity.
This first number here,
Yeah.
that is what is being influenced by the force.
Okay.
And the second number is the cause of it.
Okay.
All forces require two objects, especially in classical physics. So in the three objects on a line, so other questions before I get more specific about this problem? So I have two objects on a line, and I'm going to stick a third object somewhere so it's in equilibrium. Well, first off, I know that gravitational force is attractive. If I put my mass 3 over here, it's going to get pulled to the right. I got two, or accelerated to the right at least. I have two objects over here, it's being pulled towards both of them. There's no way it can be in equilibrium. Same with over here. There's no way it can be in equilibrium over here because it's being pulled in that direction. So it's got to be somewhere in the middle because it's being pulled both ways. So somewhere, mass 3. So there's a formality to it that I'm going to start out with a formality, then I'm going to do or you can just think through it. Formality of it is we want the force on 3, gravitational force on 3. Well, if it's in equilibrium, what would the force be?
0.
And that's got to be the force of gravity on 3 from 1, plus the force of gravity on 3 from 2. So this is the formal approach of doing it. We have a formula over there. So this would be negative G mass 1 mass 3 over R13 squared. It's squared over there, right? Yep. R1 hat plus negative G mass 1, mass 3, mass 2 over R2 3 squared, R2 hat. Now I can't just add these up, I can't just plug numbers in and just add them up because R1 hat, R2 hat have different reference points. But if I'm in the middle here, I know that R1 hat is going to the right. In the middle here, I know that R2 hat is going to the left. Over here, R1 hat and R2 hat are both going to the left. But in the middle, they're going in opposite directions, and so in the middle, one is the negative of the other. Because their magnitudes are the same, they're both unit vectors. And so I can just establish that way as positive. And so this R1 hat is a positive, so I get negative G mass 1 mass 3 over R1 3 squared plus R2 hat would be negative, so the negatives cancel out. G mass 3 mass 2 over R2 3 squared equals 0. That's the formality of it. Or the simplest way is going, I know this thing is going to be pulled towards mass 1, it may pull towards mass 2. The forces have to equal out, they have to cancel each other out. So the force this way equals the force that way. I think through the directions and I don't have to worry about all the formality of negative whatever hat. I got my mass 3 here, it's being pulled to the left with a magnitude of G M1, M1 and 3 over whatever that distance is squared. And it's being pulled to the right, G mass 2, mass 3 over whatever that distance is squared. And I just set them equal to each other. For gluttons for punishment, you would plug the numbers in that you do know and you multiply it all out. For those who want to civilize themselves, or probably the wrong word, those who want to cause less pain for themselves will cancel stuff out. G goes away, mass 3 goes away, and it just